Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we will be looking at a specific example of the effect of Coriolis force and centrifugal forces, namely how the motion, what is the motion of the fluid on the surface of the ocean, right? So the ocean currents. So what we are going to talk about are the case of the ocean currents. So the equation of motion for the steady flow of the atmosphere, the equation of motion for the steady flow of the atmosphere is given by rho A plus 2 rho omega cross V is minus rho GK minus grad P. Okay, so this is the equation of force balance. Now the equation is very similar to what we had seen in the previous module, except for this grad P term. Right, so this is an impact. So what is this new term? This new term reflects how the motion of the present particle or the fluid element or the fluid particle is impacted by the motion of its surroundings. So that is all taken care of by this extra term. So now we talk about the severity of motion or the severity of the currents based on the impact of this term versus the other terms. So as I just said, this negative grad P is the pressure gradient term. Pressure gradient term, right? And it represents the force exerted on the fluid particle by the fluid around it. So it is the force on the fluid particle by the surroundings. Okay, so what we have is, let me call this equation as 1. If we compare the length scales of 1, we see the following. We have that, let us say that the length scale associated with the flow is L. The length scale is L, and the velocity scale is V. So we see that the Coriolis effect is going to be 2 omega cross V, which is order omega V. That's the Coriolis effect, and we see that the acceleration, so this is omega cross V, so this is the order of the Coriolis term, and then the order of the acceleration, which is this term, will be V square by L, right? So that's density times acceleration term. So this is the force term. So then this one, or so what we have is that this is the order of the Coriolis term, and in general the order of the acceleration term is V square by L, and we see that it turns out that we can describe a dimensionless number based on the dimensions of these two quantities. So, which measures the order of the Coriolis force with respect to the other term. So, we have a dimensionless ratio which is given by R naught equal to V by omega L. So called Rossby number. So this measures the overall strength of the Coriolis term, compared with the other acceleration terms, right? Okay, so then what we have is, suppose this quantity is much less than 1. Suppose L naught is much less than 1. Then what we have is the Coriolis acceleration is going to dominate. So the Coriolis acceleration is going to dominate the real acceleration. Right? And the equation of motion in this case, is that is Rossby number small, will now reduce to the following. So the equation of motion will read as 2 rho omega cross v, so that's the Coriolis term, plus is equal to minus rho gk, that's the weight, and minus grad p. Right? So this is a case where the acceleration term is small, and we typically call this type of flow as geostrophic flows. Now, suppose we take a scalar product of this equation with v. So let me call this equation as 2, and suppose I take a scalar product with respect to v, then v dot grad p is 0. That's the only term that remains, because v dot del cross omega cross v is going to, that's a triple product, is going to be 0. And well, v is perpendicular to k, the vertical distance, the vertical direction, and the only quantity that is remaining after the dot product is the grad p term. So v dot grad p is equal to 0 is what we get. So what we have is, so what it tells us that this geostrophic flow, when dot product is taken with pressure, is that the velocity contours are perpendicular to the pressure contours here, right? So it turns out that the velocity so this is the case where we are talking in 2D, right? So in 2D, the third dimension is also going to vanish. So there is no k hat term. We are just talking about the motion on the level surface, the 2D. So in 2D, we see that velocity v is horizontal, and we see that if we take the scalar product, we see that v dot del p is 0, or we have that v is parallel to the pressure contours. So v here is perpendicular to the gradient of p, or v is parallel to the pressure contours, right? So the conclusion out of this whole set of steps is that the fluid flows along the isobars, or the contours with constant pressure. So which means that the fluid flows along isobars, or the constant pressure contours, right? So then So then what we have is, so in low pressure systems, in low pressure systems, let us see all these ideas with some example. So suppose in low pressure system we have, so typical example could be when the velocity of the particle is about 10 meters per second and L is 1000 kilometers and omega is 10 to the power minus 4 radians per second. So this is the so V by L. So this is V by L. This is the omega. So omega is 10 to the power minus 4 radians per second, and then in this case my Rossby number being V by omega L, Rossby number comes out to be 0.1, roughly 0.1, and we call this is a case of the geostrophic flows where the wind follows the isobars. So this is a low Rossby number case. Okay, so then typically if we look at an example of a hurricane where the wind flows, so and try to see what happens at the center of a hurricane. So in the center of a hurricane, we see that V is roughly 50 meters per second and L is 50 kilometers and R naught is roughly 10. Out of all this information, we see that R naught is 10, and that is this is a case where the Coriolis effect is small, right? So this is the case when this is the case of low Coriolis effect. Low Coriolis effect, right? This was the earlier case was the case of high Coriolis effect where the Rossby number was low, right? So this is what we said when R naught is less than 1, the Coriolis terms dominate. Okay, so this is typically the case of a center of a hurricane where the Coriolis effects are low and we do not feel the net effect of these rotating forces, right? So what is important is the center of the hurricane is typically very calm compared to the exterior. Okay, so then for a multi-particle system, we talk about the system in an non-inertial frame. So in non-inertial frame, let us now write down the equation of motion. So I am rewriting. So this is a multi-particle system. So for each particle mi, we can write the equation of motion A plus omega dot cross Ri plus 2 omega cross Vi plus omega cross Ri, right? And plus dVi dt, right? So this is equal to Fi plus summation Gij. So this is my external force, and these are the second term on the right hand side are my mutual interaction forces. Okay, so then if we sum this giant equation over all particles, so sum over all particles, we see that the equation reduces to the following: A plus omega dot cross R. So R is the net position of the n particles, plus 2 omega cross V plus omega cross R, right? Plus dV dt is equal to F, right? So these are my center of mass variables here. So R is the position vector of the center of mass and V is the center of mass velocity. So these are all center of mass variables. So this is an equation in the non-inertial frame for the center of mass of the n particle system. So then if we talk about energy conservation, we see that so energy conservation of the system of particle. So in frames with fixed origin, and constant angular velocity, we see that A and omega are 0, right? So this is the case where the origin is fixed, so there is no acceleration, and the angular velocity is constant, so no omega dot. So we see that the second law for each particle reduces to the following. We have the following now equation. So this second term vanishes and the first term also vanishes, and we are left with 2 omega cross Vi plus omega cross Ri plus dVi dt. This is equal to F plus the summation Gij. Okay, so now if we take this equation, if we take a dot product with velocities Vi, so we take a dot product with velocity Vi, let us call this equation as star. So dot product with star, the first term is going to vanish because it's a scalar triple product term, V omega V, so that will vanish, and the other equation is going to reduce, this second term will reduce as, so this is going to be Vi omega dot Ri omega minus omega square Ri. And then if we complete the dot product, so this is going to be omega dot Ri omega dot Vi minus omega square Vi dot Ri. So Vi dot Ri, and that is what we have. So now let me rewrite this term. So this term, now this equation is going to be, so this is going to be ddt of half omega dot Ri square minus half omega square Ri dot Ri. So notice the Vi, we have changed it into the formula for Ri by taking a time derivative outside this entire term. So we see that this is this quantity, and this is going to be, we denote this entire expression as ddt of, we introduce a new variable, so this is omega square times pi square, right? So then what we have is, the pi is the perpendicular distance, of p from the rotation axis, right? So this is the perpendicular distance from the rotation axis. And we see that in this case, I call this this term, so what have we got? So omega square Iij, sorry. So we have to introduce another variable Iij. So let us now introduce this term Iij, and Iij is going to be summation mi times summation xk times delta ij minus xi xj. Okay, so this is what we have. Okay, so then if we now multiply this this equation star, so this is the equation star. So if we multiply this equation star by if we sum up this equation, where it is, not star equation but this new equation double star, right? If we multiply this new equation double star by mi and sum over all I, we see the so double star multiplied with mi and sum over all I, we see that ddt of summation I from 1 to n half mvi dot with vi minus half omega square summation mi pi square I from 1 to n, right? So we have summed up, and we see that this is equal to summation fi vi. So this is the dot product, and then plus, due to the mutual interaction forces, we have the term ij gij dot vi, right? And we see that this new quantity is ddt of the kinetic energy T minus half I omega square. Let me call this I omega, because this is the moment of inertia about the axis, about the rotational axis, the moment of inertia about the rotational axis, and this is summation fi vi plus summation gij vi. Okay. So then, so if the apparent total work of the forces can be represented by a potential energy, right? If the apparent total work of the forces in 2, so if we can represent the right hand side by some potential energy, so suppose these forces are conservative, so then our relation looks as follows. So if our total work done by all forces can be represented with potential energy V, right? We see that we call this an apparently conservative system. Why apparently? Because we are looking at the system in an moving frame. So apparently conservative system. And in this case we have that T plus V. So now this is going to be represented by our potential V. So we have T plus V is equal to minus half IA omega square is equal to E, right? And this is our constant of the system. So this is the total energy E. So we have So what we get is now this quantity, this new quantity in the energy equation is the so-called centrifugal potential energy. Centrifugal potential energy, and that's about what we wanted to say. Okay, so at this point I am all out of time. Well, all the concepts are quite over when we are talking in terms of this rigid body dynamics, at least the concepts in physics. And in the next module, we are going to look at the concepts in mathematics, which will be needed eventually to look at the motion of these complicated rigid bodies. So thank you so far for listening.